So again, more terminology and concepts. You may need your yellow, you know what, I'll let you know if you need your yellow formula sheet. I think today is mostly terminology and concepts. So lesson 3, distance and displacement. I alluded to this last lesson, but now we're going to formalize it. It turns out, Max, in physics, every quantity that's measured is either a scalar or a vector. Every physics quantity that's measured is either a scalar or a vector. And one of the things that you'll memorize is whenever I introduce a new concept to you, whether it's a scalar or a vector, but you won't have to go out of your way to memorize it. In doing the homework, you'll just clue in. Scalars have magnitude, that's the fancy word for size, only. Scalars have magnitude only. For example, time. Mass. Volume. Speed, distance, energy, work, voltage, magnetic field. No, magnetic field is a vector. A bunch. Vectors have both magnitude and they have a direction. And that's going to become important. For example, velocity is going to be a vector. Force is going to be a vector. It matters which direction you push things. If I push this way and this way, that's very different from pushing this way and this way. They'll have very different results. But if I weigh something, it doesn't matter. If I add 10 kilograms and 10 kilograms, it's always going to be 20 kilograms. But if I push 10 newtons left and 10 newtons right, the answer is 0. If I push 10 newtons left and 10 newtons left, the answer is 20 newtons left, even though there's still 10 newtons. Direction makes a difference. Velocity, force, for what it's worth, momentum is a vector. These are all concepts that we'll be looking at throughout this course. So I have a chart. There are some quantities that can be both depending on how we refer to them. And as an example, speed. Is a scalar. What's the speed limit on the Lougheed as you're heading out to the Pitt Bridge? 80 what units, please? Okay. 80 kilometers per hour. That has a magnitude, but that tells you nothing about how the person is traveling. Velocity is a vector. 80 kilometers per hour due north. That's a vector. It has a magnitude, 80, and a direction, north. Okay. Distance is a scalar. All distance wants to know is how far, or how long, or how big. How far from Pitt Meadows to Vancouver? 45 kilometers. Around. Displacement is a vector. Displacement is a vector. How far from Vancouver to, or from Pitt Meadows to Vancouver? 45 kilometers at 12 degrees north of west. By the way, that second phrase, you'll learn how that works towards the end of this year. Don't freak out. So speed and velocity are the same thing, speed, scalar. How can I remember that speed is a scalar and that velocity is a vector? You know, if I was a good teacher, Thomas, I'd have some dumb, easy way for you to remember that speed is a scalar and that velocity is a vector. I got nothing. I suck as a teacher. Then there are some that don't have a mirroring component. So time is always a scalar. Well, I was watching a movie where they went back in. No, that's sci-fi. No back in time. No negative time is a scalar. No direction. Acceleration's a vector, although often we're going to be sloppy, Amy, and just say, find the magnitude. And you'll kind of figure out whether the question wants just the magnitude or whether it wants you to come up with a direction. Usually this year what we'll say is, you know what? If you're giving me the answer as positive, you're telling me we're speeding up. How would I show that we're slowing down? Negative. Other ones that we'll look at that are scalars, work, energy, we'll get to those this year. Other ones that we'll look at that are vectors, force, momentum. Justin, what we want to have now is some easy shorthand way that I can communicate to you that this is a vector and that this is a scalar. In textbooks, it's done by putting vectors in bold font. So that's a vector, but this is hard to do in handwriting. Okay, there, that's a vector. So instead, we put an arrow above a vector. Look up. Speed, velocity. Speed, velocity. Oh, and we've gotten lazy over the years. We used to put the full arrow in, but you know what? We just do that, kind of and a half arrow. And that's how you can tell. Will I ever take marks off if you're sloppy on notation? Probably not, but what I will try and do in our notes and in our homework is emphasize when it's a vector, because the math is different. Put your pencils down. So we have to be careful with vector math. Distance versus displacement. Let's get a little formal. Distance is very simple. It's how far an object has traveled. Symbol. The correct symbol for distance is an S. It's from Latin. Problem. What number does that also look like if I'm really, really writing quickly? a 5. And what units of time does that also look like? So even though that is the correct variable, cross it out. We're not going to use it. If you go to university and you take physics, you might have some profs that use the S. That's a British thing in particular. Another variable that's sometimes used for distance is x if you're talking about a horizontal distance, because that works like you're on a graph. Fair enough. Put an x through the x. I'm not going to use that either. I'm going to use the wrong variable, but it's easier to use in Physics 11. I'm going to use the letter D for distance. D is totally wrong because the letter D in calculus actually has a hugely important meaning. If you put a D in front of something in calculus, that's telling you to take a derivative, which is a hugely important. You know what, though? For now, in Physics 11 and in Physics 12, we'll survive without calculus. But I got to be full disclosure, D is wrong. But it's what's used in high school more often than not. Wink, wink, nudge, nudge, understanding that if you go to university, we'll correct it. How do you know that's a scalar? What don't you see written above it? No arrow. Displacement is an object's change in position. So if you think about Alexa's little demonstration that he did earlier, when he went 2 steps forward plus 2 steps forward, his change in position was 4 steps forward. When he went 2 steps forward and then 2 steps backwards, what was his change in position? 0. That's a displacement. What distance did he travel? 4, because he took 4 steps. See the difference? Okay. Symbol, again, technically, don't write this down, but no one uses that, or no one uses that. We're going to use that. I shouldn't say no one uses that. In high school, we choose not to because it's confusing. So, let's imagine a little bug, and it's walking along the number line, so it's walking in meters. There's my high-tech drawing. It starts at A, right there, walks to B, then turns around and walks to C. So if you want to, you can draw a little line like this, and then above it, you can draw a little line like that. That's how I can kind of show a before and after, a part 1 and a part 2. What distance did the bug walk? D equals? Well, what was the distance from A to B in your head, please, by looking at the number line? 4 plus. What's the distance from B to C? 10. In your notes, write this down. In your homework, if you can do this in your head, great. But just so that when you're studying, you know what the heck we got. Write 4 plus 10. And in your head, 4 plus 10 is 14. Units. What was the distance measured in meters? Bug walked 14 meters. Ah. What was the bug's displacement or change in position? Where was it when it started? Where did it end? What's its change in position? So, sorry? Not -2. We started here. We ended here. We don't care about what happened in between. What? You just saw it. What is it? -6. What's the negative telling you? Well, you could also have said 6 meters left. Which one's less writing? Let's use the negative. It's more convenient. Okay. By the way, negative being left, though, math is totally arbitrary. We could let negative be to the right. You'd have to have a good reason to, but you'll find in Physics 12, often we'll let the more convenient direction be positive, whether it's left, right, up or down, we don't care. We ask what makes the math easier. In Physics 11, usually up will be positive, down will be negative, right will be positive, left will be negative. Speeding up will be positive, slowing down will be negative. Forwards will be, backwards will be, okay? We'll usually stick with that. It's a good notation. Speed versus velocity. Turn the page. Average speed equals change in distance over change in time. Oh, where delta equals change in. As an equation, V equals d over t. What would the units be? Well, you've probably memorized this, but if you ever blank, you can figure it out. Distance. What's our fundamental measure of distance in physics? Think metric. You're right. Meters over. Can you see how meters per second is hidden in distance over time? In fact, can you see how distance over time is hidden in the units if you blank on the equation and you don't have your handy-dandy formula sheet handy? Scalar or vector? Well, distance, scalar or vector? Yeah, Kyle was clever enough to go look at his notes because he forgot. Good. Distance, scalar. Time, scalar or vector? I'm going to tell you right now, scalar divided by scalar gives scalar. Now, that's the physics proof. You could also have said, hey, Dueck, did you put a stupid arrow over the top? No, then it's a scalar. Speed. Average velocity equals now remember, when I put that arrow above a D, it's not distance. What is it? You can even make a little note. Again, where delta equals change in. As an equation, it doesn't look very different. It says it looks almost identical, but can you see the amount of information that's contained in the notation? This is saying you're going to get a vector answer, and you better have some vector inputs. By the way, why didn't I put an arrow above time? Time is always a scalar. Oh, but for what it's worth, if you're trying to learn rules, vector divided by scalar gives vector. For what it's, but we're not going to get that high tech. Units, still meters per second. This is the vector. Okay. Example 2. If the bug's trip mentioned in example 1 took 2 hours, what's the bug's average speed in meters per second? I got a problem. What do I want the speed units to be in? What did I say? Meters per second. What unit of time did I give you? Hours. We got to do a conversion. You know what? Let's draw a little arrow. 2 hours. How do I go from hours to seconds? I don't know. What can I turn hours into? Oh, so let's go. We want the H to cancel. Minutes on top. Alexa, how many minutes are in how many hours?
60.
Minutes are in
1 hour.
Okay. Now we're in minutes. That's a good. Oh, but we want to get to seconds. Alexa, what can I convert minutes into? Have I got my conversion factor? Nice. So minutes on the bottom, seconds on the top, and it's again a 60 to 1. What's the shortcut? never mind, no, it wasn't you. It was Devin that had the shortcut, and he's away. Can you see? If you want to, you can, if you want to, and you don't need to, you can choose to memorize, there's 3,600 seconds in 1 hour. I don't have that at my fingertips. I usually remember it whenever I teach this unit, but if you ask me in May, I have to rederive it. Okay, so how many seconds are we actually talking about? What does T equal? 2 times 60 times 60. You might need a calculator, or you can do it in your head. 7,200, okay. What was the, for A, do I want to use distance or displacement? What are they asking me to find in part A? Average what? Speed. Oh, so am I going to use distance over time or displacement over time? Distance. So am I going to use 14 or am I going to use -6 from the previous question? What's the distance that the bug traveled? 14? So average speed is going to be 14 meters divided by 7,200. You're going to get a small answer. It's a bug! You should get a small answer. They're not fast. You get 0.019444444. I'm not going to write that. I'm going to go scientific notation. First of all, for what it's worth, how many sig figs? Well, that's sort of 1 sig fig. That's 2. You know what? I'm going to just arbitrarily go to 3 sig figs because I want to get the 4 in there. So this is going to be 1.94 times 10 to the negative what? See it? Right? -3. 1.94 times 10 to the -3 units. Or around 2 millimeters per second if you want to put that into some context. Every second it's traveling about, what's 2 millimeters? About like that, right? It's a slow bug. Snail, slug, I don't know, it's slow. What's the bug's average velocity? Okay. Velocity is going to be displacement over time. What was the displacement for the bug? Wasn't 6. Got to have a directional component as well. The time is still 7,200. So I'm going to get a velocity of -6 over 7,200. What's the negative telling me as a direction? No, that'd be for an acceleration. This is a velocity. We're assuming it's traveling at a constant speed, actually. What's the negative telling me as a direction? Left, sure. Or backwards, but let's assume, I don't think bugs walk backwards, so let's assume it turned around. And I think I did I say turn around in the question? Please tell me I did. Yeah, good. I said turns around, so it's always walking forwards in terms of pointing its head in the same direction that it's walking, but it's walking left for more. So let's write this down. My calculator gave me an answer in scientific notation. I don't know if yours did. Mine is -8.33 times 10 to the -4 meters per second. Is that a vector? Yes, the negative contains a direction. Again, or you could write 8.33 times 10 to the -4 meters per second. Left. Which one is easier to write? Okay. Here's where I would get fussy. Can you all look up? I would put a frowny face. Can you all look up? Amy, you too? Can you all look up? Look up. I need you to watch. If you did that, Because now you're saying it's negative left. What would negative left actually be? Right. So don't go over with direction. One or the other. I suggest using the negative. Next page. Jason is giving Peter a football play to run. This is from Foxtrot Comics. I love Foxtrot Comics. First of all, the author, Bill Ammond, actually has his physics degree. In fact, while he was in university, he was doodling all the time while he was getting his physics degree. You gonna make it? Yeah? And his prof suggested, hey, you should publish some of this. Also because the youngest boy, Jason, is really nerdy, and I can empathize with that. So you ready? Here's the football play. Okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards, then turn right and go 25 yards, then turn right again and go 30 yards, then turn right and go 30 yards, then turn left and go 10 yards. Then turn left and go 15 yards, then turn left and go 20 yards, then turn left and go 50 yards, and I'll hit you with the ball. His older brother Peter thinks for a little bit. Won't I be right back where I started? Jason says, I can't throw very far. Peter says, okay, here's a new play. I never get to be quarterback. We have, if it wasn't so cold outside, I would take you guys out. We have run this play in the field. The math is correct. You do end up back where you started from. So, what distance will Peter run in order to complete this play? Distance doesn't care about direction. Distance only cares about how many yards. So it's going to be 40 yards. Then, what's the next one? 20. Then 25, I'm just reading from the question, right? Then 30, then another 30, then 10, then 15, then 20, then 50. Did I get everything? 40, 20, 25, 30, 30, 10, 15, 20, 50. You might be able to add that in your head, or you could use a calculator. I don't care. What's the answer? Don't all rush for your calculators at once or anything. Sorry? 210 yards. I guess it's yards because we're in the U.S. Okay. What will his displacement be if he ends up back where he started from? 0. See the difference? So what's your homework? You're going to need a ruler with centimeters on it for your homework. If you don't have one, I still have some behind Cameron on the table there, but make sure you return it at the end of class. So if you need to get one, grab one now. So for those of you watching on YouTube, apparently I have a student who doesn't know how to use a calculator. What do you say, 240? 240 yards, not 210 yards. I'm guessing you missed typing the second 30 in. Just a thought. What's your homework? Can you take a look at this, please? This is called distance versus displacement and speed versus velocity. We're going to do one question together, and then I'm going to turn you loose. You'll probably get it all done in class. If you finish it in class, great. So below is a map of a happy country that lies deep within the subconscious of crazy physicists. Thank you. Whenever they feel stressed out, like you just did, or sad, they go to this country and they ponder kinematics problems as they travel from one happy town to the next. Did you guys remember Bob Ross, the painter on PBS with the big afro that always did the happy little valley and the happy little tree? You guys missed out. If you ever watch PBS, he died a few years ago, but they still run it on PBS. He's a painter and he's, uber hippie. So here's our happy little town. It will make you feel happy too. So here's what I've done. I've given you road what? Not displacements, distances. The distance is the curvy long path, which is tough to measure, so I did that for you. Apparently instead of trying to pronounce these, I'm going to go from F to Q. The length of this curvy road is 75. From F to Z is 28. Okay? These are the distances. Now, on this map, Each centimeter is 1 kilometer. So with your ruler, can you all measure the displacement from F to Q, which would be that line right there? Except better than that. I can't measure it up here because mine is much, with my projector, my numbers will be much bigger than your numbers, so I can't do this, but what's the displacement from F to Q? Yep. 3.25 centimeters, which is 3.25, I think so, okay? So just for one more practice, by the way, 3.25 is almost impossible to, I would say 3.3 or 3.2. I'll take, there's going to be some variation, okay? Is he right, by the way? I should have asked. We'll call this the Thomas consequence. Is he right? 3.3, okay. Hey, measure the displacement from Z to G. From Zorkbaum to Glurknoid. Just again, so that you know your ruler is accurate. Yes, Spencer, you too. What do you get? 5.3, 5.2, 5.4. I mean, there's going to be, you know, it's even. Oh, did you put it on the middle of the dot or on the end of the dot? Or there's lots of there's some variation. Okay, so 5.3, which would be okay. So you need a ruler with centimeters on it for this exercise. For each of the following, find the distance in kilometers, the magnitude of the displacement in kilometers. So the distance, you'll just add up the road lengths. The displacement, put your ruler on the first town, ruler on the second town. Yes?
Under the picture, it says the scale is 1 centimeter to 10 kilometers.
Ah, thank you. So that says it on your picture? Oh, there it is. 1 centimeter is 10 kilometers. So 3.25 is 32.5 kilometers, or 33 kilometers. Thank you. I got that somewhere. So find the distance traveled, find the magnitude of the displacement. This is going to be, come on, pen. Come on, pen. Sorry, let's try that. This is going to be using your ruler. This is going to be just adding. Find the average speed. Now, average speed, symbol V, is the distance over the time, and we'll go in kilometers per hour. So the times I'm going to give you are in hours, and the distances that you're going to get are in kilometers. And then find the average velocity, which is going to be displacement over time. And displacement is going to be measured with your ruler. Clear your all your work and calculations on a separate piece of paper. Staple it to the back. And I did attach the answers here. Again, you could be plus or minus 0.1. It's all in how you hold the ruler. Okay? You'll probably finish it in about 15 minutes. I got a video I'll be throwing on in a little while anyways.